We're going back to limits. Well, chapter.
Go back to integration.
No. Chapter 9, sequences and series and convergence and divergence, all that stuff. So this is a little bit of a preview towards that before we completely get away with derivatives and integrals and whatnot. So it has a little bit of that involved, but L'Hopital's rule does a couple of cool things for us. We're going to look at just a couple of versions of it today, and we'll probably wrap up a couple other versions tomorrow. So we're not going to. L'Hopital's can really kick your butt if you do it all in a day. So we're going to split this up in a couple days. Oh, and by the way, I'll get to that in a second. So L'Hopital's rule. Let's go back to just some limits, refresh our brains of how how some of these limits work. If I go x approaches like 1 of x plus 1. Yeah, just 2. Pretty straightforward, pretty basic, not too bad. I hope. Pretty easy. Now what happens if you go x squared and then over x minus 1?
Oh, no.
You can't factor the top.
Long divide.
You plug in numbers.
You could long divide, yep.
You plug in numbers really quick.
Plug in that, yeah, what you were supposed to do is plug in numbers really close to 1. So plug in like 0.9 or 0.99 or 0.99 or 1.1 or 1.01 or 1.001. Anyways, kind of a waste of time, right? Let's say this happened to be a minus right here, right? And we could do some tricks with it. I know I hate changing it on here, but
Factors.
But now you can factor and cancel. Now this particular one that I have written here, this lends itself to L'Hopital's rule, and I'll show you. There's a couple ways to do this, and then the ones we do today, you probably can do most of them either way, so it doesn't matter. But it's kind of a cool trick. And on other ones, you have to do it this way. So, anyways, on this particular one, you would factor the top, so you would go limit as x approaches 1, and you would go x plus 1, x minus 1, and then divide that by x minus 1, and then your x minus 1's cancel. And all of a sudden, you're back to that original one that we already had. You can just plug the 1 directly in, direct substitution, and then you get 2. So your limit for this one would be 2. Even though that would technically be a hole in the graph. Okay, this graph, not exactly sure what it would look like. Probably look like a line, x plus 1 is my guess. So that means you're going to have some line like this. But at x equals negative 1, you're going to have a hole right there. So as you approach it from this side, we're getting to a value of 2. I guess I wrote that wrong.
X equals 1.
As you approach 1.
Oh, it was x approaches 1, not negative 1. Thank you. Sorry. Same graph. But as x approaches 1, that right there, a hole, it goes to looks like 2. Okay? So, anyways, that was kind of the ballpark idea of what graphs we're doing. Now, the problem with this right here, this very beginning, this is how you can tell whether or not you can use L'Hopital's rule. So this is one version of it. If I were to plug in a 1 right there, if I were to plug in a 1 in the top, what would you get? You get a 0, right? Divided by a 1 in the bottom, you get a 0, right? They call that an indeterminate form. So, indeterminate. If it's 0 divided by 0, that's always one of those weird deals. It's like something fishy's going on. If it's 0 divided by 0, you can use L'Hopital's rule. Now, L'Hopital's rule is a pretty fast thing to do. It's a very slick way to do limits on some of these limits. But you can only do it if it's 0 over 0, or if it's a couple other versions that we're going to get to a little bit later. But the first one is that we're going to look at is 0 over 0. Okay? The second one is if we did limits as x approached infinity. And that was basically horizontal asymptotes. What's the graph doing on the far right side? What's the graph doing on the far left side? Okay, so let's say we had some function like, I had one written down. Oh, there it is. Okay, thank you. 3x squared minus 1 over 2x squared plus 1. Now, there are some nice shortcuts to these ones in some cases. Sometimes they're nice. If they're polynomials, it's usually pretty nice. But on this one, as x goes to infinity, you're plugging in a really big number. So on the top right here, if you plug in infinity, you're squaring it, times 3 minus 1. The top number is pretty much going to go to infinity, right? It's going to get really big without bound. If you plug in infinity on the bottom, right, we have infinity squared, still infinity. And then the times 2, still infinity plus 1, so still infinity. So we have infinity over infinity. This is the second indeterminate case that we're going to look at today. So if it fits in one of those molds, either 0 over 0 or infinity over infinity, we can use L'Hopital's rule. Okay. Now there was a nice shortcut for this one. Do you guys remember what that is? It's just 3 halves, right? If those two match right there, if they're both x squareds, then it's just the coefficients in front of them. And the reason that is, and I don't want to get too overbound with what we've already done in the past, but what you really should do is divide everything by an x squared. So it would be 3 minus 1 over x squared divided by 2 plus 1 over x squared. And then if I plug in infinity, 1 over a really, really big number is 0. 1 over a really big number is 0. So these pretty much just go away to 0, so it's 3 over 2. So that's why that one does equal 3 over 2. So that's like a horizontal asymptote. As you plug in a really big number on the right, that means at 1.5, you're going to have some line that the graph is going to get really close to all the way on the far right side. Okay? So anyways, that's kind of just some background stuff that you need in order to do L'Hopital's rule. It's got to be in either this form today or this form today. Those are the two main forms that we're going to look at. L'Hopital's rule says this. It says that if I'm taking the limit as x goes to c, does that look a little fuzzy? Of two functions, so let's say I got f of x and then divided by g of x. I'm going to put a big equal sign. Equals, because this is L'Hopital.
What?
Okay, so this function, apply L'Hopital's rule. Apply L'Hopital's rule. That's a good way to write this. And really that's going to be the same as taking the limit as x approaches c of the derivative of x divided by the derivative of g. No, there's no s in it.
Yeah.
Oh yeah, there is.
So, and they kind of think that he's important, so they try to get his name right. They think he's like super important.
Oh, he's dead.
Dead people can be important too. Dead people can be important too.
Yeah.
All right, so the limit as x approaches 1. I'm going to go back to ones that we've already done. X approaches 1 of x squared minus 1 divided by x minus 1. I think that's the one we just did. We already know the answer to it. It's above in your notes. Not a big deal. But this right here, if I were to plug in a 1, just direct substitution, I would get 0 over 0. So this is a 0 over 0 case. So this is one that we can apply L'Hopital's rule on. Okay, so L'Hopital's rule, I'm going to just do a big equal sign. LHOP, we'll abbreviate. I'll give him a little bit. So the LHOP, basically what you're going to do is you're going to take the derivative of both those functions individually. Now that's kind of the trick here, is taking the derivative of both of those individually. You're not doing the derivative of the entire function, right? Because then you have to do quotient rule. And it'd be way harder. Okay, we're not doing that. You don't have to do that. All you have to do for L'Hopital's rule is take the derivative of the top function and the bottom function. So the top function derivative is 2x. The bottom function derivative is 1. So if I plug in direct substitution now, plugging in a 1, I get 2.
Oh.
You've been holding this out.
Yes.
I know, because factoring that and canceling is so hard. I'm sorry. It takes forever.
When it got a little more difficult.
Some of the derivative, obviously, they're going to get a little harder. Yeah, so they're going to get a little more challenging. And I'll show you some of it a little more challenging. But that's how that works. Now, it also works, yeah.
So what if you do that L'Hopital or whatever,
Yeah.
and then it happens again where you can't do it?
Good question. Like on the one that we just did, the other one I think was one of those cases, right? Limit as x approached infinity of 3x squared minus 1 divided by 2x squared plus 1, right? If we applied L'Hopital's rule to this, we know the answer is 3 over 2, so obviously that's a faster way to do this. But if we were to do L'Hopital's rule, if I plug in infinity, this is an infinity over infinity case. This is an indeterminate case right here when I plug in my infinities. So if I just take the derivative of the top and the bottom, so I'm going to go L'Hopital right here. Okay, so derivative of that is going to be... I know. Well, eventually I'm not going to write anything because they're equal. I mean, they're equivalent. So anyway, so take the derivative of that would be 6x divided by, looks like 4x. Right, which still, this is still an infinity over infinity indeterminate form, right? So we just do it again. Okay, so you can do L'Hopital's rule over and over again. Doesn't matter how far into the derivatives you can go. Well, the derivative of both of those is 6 over 4, which gives you 3 over 2. Okay? So the exact same answer.
Do 0 over 0 is
I didn't hear that.
Do 0 over 0 is infinity over infinity.
Yeah, they happen a lot. Yeah. The 0 over 0 is an infinity. Like your whole assignment tonight will be that, but we did a lot where we had to do it like a super, super harder way. I can, where this is going to be a sweet way to do it. Yeah. Where this is going to be the golden way to do it.
How is this part of this section?
I know. Because it's honestly it's previewed for chapter 9. That's what they're done. Because like there's two sections at the end of 8 that are more or less previews for chapter 9, but they weren't enough to make it its own chapter, so they just said, all right, we'll throw it at 8.
Just randomly.
My opinion. That's my opinion. I don't know if yours.
And it also saves paper probably.
What's that?
It also saves paper.
It also saves paper.
Your ink
They don't
there.
have to give it its own chapters. It's like
Yeah, they're just saying. Yeah, you don't have to have the review problems in the back. You know, well, I guess it's not.
Well, they don't have an introduction.
Which one was it? Oh, I was saying that one.
And true.
That's the color page too.
Yes.
Color copies are expensive.
We would love to actually.
Okay, now for tonight, what you do want to check, you want to check to make sure that it is an indeterminate form, which means 0 over 0 or infinity over infinity. It's got to work. It's got to be one of those. If it doesn't, then it's not going to work. Very nice. It might work every once in a while. This one should work, hopefully.
8 is 0.
Yeah, what form is this? This is a 0 over 0 form, right? So that's the indeterminate. This is 0 over 0. Okay? If I plug in a 0 right there, this says to 0, e to the 0 power. Anything to 0 power is 1. 1 minus 1 would give me 0 in the numerator. Denominator is 0. Okay, so this is a 0 over 0 form, which means I can take this guy, and go ahead and do L'Hopital's rule, take the derivative top and the bottom. Not quotient rule. I can't stress that enough. A lot of people are going to try quotient rule on that, which I don't know why. It's way harder.
I don't get how
Like,
I
don't
know.
do more work than you have to. So derivative of the top would be, I think, 2e to the 2x.
Yes.
And then divide this by 1, hopefully.
And then it equals to.
Okay, now we're going to plug in a 0. We can just straight evaluate this now. It's not in an indeterminate form, so I don't have to do it again. Plug in a 0 right there. Let's see, this would be 0 e to the 0 is 1. 1 times 2 gives you 2. So this would equal 2.
So what does this find you?
This finds you the limit as x approaches 0. So if you were to graph this big mess, and you got some graph that goes like this and you have a hole right here, as you're approaching it on this side and you're approaching on this side, you're getting that value right there. That's what you're looking for.
Is there some sort of measure for this?
Your x value is 0.
That's your Y value.
Yeah, that's your y value. That's your y value. So it's how tall it is, basically. What's the proof of this?
How do you figure
Proof
this out?
is not nice. It's in Appendix 2. I was looking at it, and it's actually not hard to follow, but it bugs me how they do it. Like they're like, all right, I want this as my nice answer, and then they work backwards to a function that they can just say, oh yeah, I'll start with this. So then they say randomly, oh, I'll start with this, and then simplify it down to L'Hopital's rule. It drives me crazy. It's like, how do you? It's like I think how they word it, there exists a function such as this, and then they prove it. It's like, what? And then the function means absolutely nothing for anything. It drives me crazy. So, anyways, I'm not gonna. It's kind of like one of those proofs. Exactly. It's like I want to get there, so what do I got to do to get there? It's not as powerful. Not quite as powerful. We could do a couple proofs. There's some good proofs out there. Anyways, are we getting the idea, the flavor of this? Hopefully.
Do you have any limits?
I hope. It's orange flavor today. All right, one last one, and we'll call it good for L'Hopital's for today. Okay.
Let's pray for not trigonometry.
I don't have another practice one, but I have. Well, I have a bunch of versions, but
That's what I caught of it.
so you have your one practice one.
Sorry. But I don't know the answer.
Oh, you don't? Oh, yeah. I get it. Okay, first find out what kind of form this is. If it's 0 over 0, infinity over infinity, or neither.
Xfinity. Wasn't it? I don't know.
If you guys do an infinity approaching infinity.
Oh wait, that's negative infinity on the bottom. Maybe it's infinity over 0.
I wrote it down wrong.
Yay!
Sorry.
Makes sense.
That would have been hard to do.
Yeah, it would have.
All of a sudden, that wasn't working out quite right. Okay, so figure out what form it is.
Infinity over.
And it can be negative infinity over negative infinity. It's going to be a fraction, so it fits L'Hopital's rule, though.
So if you have like x squared
It's a circle.
x, or times e to the x,
That's tomorrow.
we could just make it a fraction and then we float with it.
Yeah.
Just like that.
I don't know, it's going to be a lot of infinity.
That's one of the cases tomorrow.
A lot of infinity.
No, because the infinity on the bottom goes to the top one.
So, all right, here we go. So if I plugged in negative infinity, you square negative infinity, it's positive infinity. So the numerator has to be infinity. divided by the denominator is going to be negative infinity plugged in there, so that's a negative infinity, so positive infinity, and then e raised to the infinite power is going to be infinite, so that's going to go to infinity. Infinity over infinity. So it fits our form. It fits the criteria that we have. What's that?
Whether it's positive or negative.
Yeah, the fact that it's going on the left side of the graph, because sometimes graphs might, sometimes a graph might do something like this, but only the left side has an asymptote that it's going to as you're going to the negative. So, anyways, on this particular one, it does fit the form, so you go ahead and just do L'Hopital's rule on this one. So this equals, take the derivative of the top of the bottom, so that would be 2x divided by a negative e to the negative x. It's kind of weird taking the derivative of something in the denominator, because usually you're used to pulling it up and doing stuff with it. And just ignore it. It's going to honestly probably give you bad habits. But. Now this one is actually still in an indeterminate form, right? I get negative infinity on the numerator, and I get negative infinity in the denominator. So I actually have to do L'Hopital's again on this one. So you just keep going over and over again until you get down to something you're happy with. So on this one, you're down to 2 on the numerator, and then the denominator is going to be a e to the negative x. And so you get infinity in the denominator, right? So you get 2 over infinity. So what's that going to go to? 0. 2 over a really, really big number is going to go to 0. So eventually that's going to go to 0.
So you can never bring that e to the negative x up.
I know you don't like it, Blake, but if I go 5 divided by...
I got it.
I didn't do enough.
You should have done 1 over.
Yeah, this is 1 more 0. You
Wait,
You gotta put one in the front. You gotta put a 1 in
I'll get there. Chill. It'll all be good.
So many zeros.
Can you just hold the 0 down?
No.
Or you could put like that number raised to a caret or something.
Oh, no, it's going to be better if I go 5 here. Ooh, I'll square it. I win. It wouldn't be in L'Hopital's rule. That's what I was going to say. So you can't use L'Hopital's rule.
I like the
It would give you.
We should stage this for
Or e to the negative 3.
Because